If you're modeling complex time series data, you've likely run into a brutal wall with factorial hidden Markov models. They're incredibly powerful because they track multiple independent hidden processes simultaneously, but they suffer from a severe curse of dimensionality. Every time you add a subsystem, the state space doesn't grow linearly, it multiplies. If you naively convert an fHMM to a standard HMM, you have to Kronecker product the transition matrices into a single monolithic array. Forward filtering, the algorithm that computes likelihoods and decodes states, then balloons to an O of n times m squared complexity, where m is the product of all subsystem sizes. For even moderately sized systems, that's a memory and compute nightmare. A recent study solves this by abandoning the flat vector approach entirely and leaning into tensor algebra. Instead of flattening the dynamics, the authors keep the model in its native multidimensional structure. They replace standard matrix vector multiplications with tensor contractions and mode K stretches. The math exploits the fact that independent chains commute, allowing the filtering recursion to factorize directly across subsystems. Here's the technical shift. Instead of computing the forward pass on a giant transition matrix, they operate on tensors where each time step applies successive mode K products across the individual subsystem transitions. This avoids ever materializing the full joint state tensor. The asymptotic cost drops from O of n times m squared to O of n times m times the sum of the subsystem sizes. For k equals subsystems of size r, you're looking at a reduction from O of n times r to the 2k power, down to O of n times r to the k plus 1 power. That's not a marginal improvement, it's an exponential speedup. Benchmarks confirm the tensorized version is numerically identical to the naive approach down to machine epsilon, but runtime improvements hit up to 4,500 times faster, with drastically lower memory overhead. This makes large-scale fHMM inference viable for everything from single-molecule biophysics to financial volatility modeling. And critically, it unblocks non-conjugate Bayesian inference, where evaluating the marginal likelihood for Metropolis-Hastings sampling has historically been the bottleneck. If you're working with high-dimensional latent state models, tensorized filtering isn't just an optimization. It's a prerequisite. Check out the full derivations and implementations to see how multilinear algebra is reshaping scalable time series inference.